Welcome to lecture 19. So we'll discuss a few of the basic issues in real-time operating systems. So in many embedded devices, particularly these days, the kernel of the real-time operating system is not stored in the hard disk because, as we have argued in lecture 18, the hard disk does not provide good real-time guarantees. So there is actually a need to store it in flash memory. So it may be necessary to have DRAM, the reason being that typically the read performance of flash memory is not all that bad, even though you don't want to access it very frequently. So that is why it is often necessary to have some amount of dynamic RAM along with the flash memory. Otherwise, what we will see is that the memory access times would become very high. So what is flash memory? So flash memory is basically a persistent memory in the sense that if we turn off the power, the data kind of disappears in a DRAM, right? But in the case of a flash memory, if we turn off the power, then the data still remains. All right, so this is why it is known as a persistent memory. So in the older days, we used to call it as also an EEPROM, in the sense electrically erasable and programmable read-only memory. But again, if it's programmable, it's not read-only, right? But you need to give this much of a leeway to history. So what happens is that in a flash, you can write or erase a full block of data. So basically, the idea is that you can't access data in, let's say, small chunks of 4 bytes or 8 bytes, but essentially you access data in bigger chunks known as pages, which can be as much as a kilobyte. So that's why you would need uh, a piece of DRAM along with the flash. And also the other thing is that you can read at the granularity of pages. You can also write, but once you have written, you cannot rewrite. So then what you have to do is you have to take a block of pages. So it's known as a block. The entire block has to be erased in the sense that the entire block you'll sort of have to fill it with all zeros and then rewrite the entire thing. So what is done is whatever is like semi-written, that is transferred to a new empty block. This block is erased, and then there is kind of a transfer back, or let's say in a new empty block, whatever page you wanted to write to, you put in the modifications and you write to that page. So this is what makes kind of writing a rather slow operation in the case of flash memory. And also flash memories have a limited shelf life in the sense they support a maximum number of what is called a write and erase cycle, right, where you erase it completely and you rewrite. So only a there is a maximum cap. After that, the memory tends to wear out. So let me clear off the ink on this slide. So the way that actually we store data, and that too persistently, is basically by using a special type of transistor which has two gates. It's known as a floating gate transistor. So what happens is that it is possible to apply a strong voltage at the gate of the transistor, pull in electrons and store them over here, right? So this is known as an avalanche injection process, where a lot of electrons can be stored, and then of course they remain there. So that sets the state of the transistor. So electrons are trapped in a floating gate. So also what we have argued is to write to a byte or to write to a page, we have to create a new block where the old block is copied lock, stock, and barrel, right, to the contents of the new block. And of course, there is a directory at the top which, given the logical address, if let's say previously it was pointing here, now it's going to point here. And let's say if a given page is being modified, we add in the modifications and the modified page is written over here to its corresponding location in the new block, right? So this we have discussed. So of course the idea is that we have the notion of this floating gate transistor where large voltages are applied to either kind of suck up electrons up towards the gate and trap them over here in the middle, or you can apply a negative voltage to push them back into the channel region, right? So this is a typical NMOS MOSFET with the source and the drain, and you can see the channel region over here. So the key point is that this control gate, so we have two gates over here, right? The first is the control gate and the second is the floating gate. So the floating gate is the one that actually stores the charge. So if I were to look at a slightly detailed diagram of this, so we see the drain and source of the MOSFET, and then what you see is that we see the floating gate which stores the charge, right? If the cell is programmed, so if charge is stored here, the cell is said to be programmed, and then we have the control gate. So typically what happens is that when you have such transistors in a matrix or what is known as an array, so the control gate is enabled or programmed by a line known as the word line. So because of course this is for one bit, but you could have many such bits in a page. So all of them are stored in one row, and all of them can be, so sorry, all of them, I stand corrected, they're not on one row, they're in separate rows with different word lines. So the role of this word line is to control the control gate such that either electrons come up or they come down. And of course, whether a cell is programmed or not, so this of course can be found out because the electrical properties of the cell change if you have electrons trapped here or not, right? So in this case, this is quite easy to find in terms of the current voltage characteristics of this transistor. So as I said, flash programming is done this way, that the channel is turned on when electrons are basically flowing from the drain to the source. Sorry, electrons flowing from the source to the drain. But the avalanche injection happens when high energy electrons will jump through the insulating layer into the floating gate and kind of get trapped over there. So the read speed is not all that different from regular main memory or DRAM. It's still of the order of nanoseconds. But it is pretty much the writes, because writes, as we have said, is a complex operation and writes are what are slow. So that is why we need a DRAM in front of the flash device such that it can provide some degree of determinism to the writes. And ultimately, in a real time system, this is exactly what matters. So again, for writes, we need to generate high voltages, typically between 5 to 15 volts, to either suck up electrons or push them back. And nowadays, of course, we have multi-level flash technology where instead of this storing a boolean value, it can store a 2-bit value, which means that we can store different levels of different number of electrons in the floating gate depending upon the voltage that is applied. So the key point is that with such hardware, so we have primarily been talking about memory technology over here, but with such hardware, which includes hard drives, flash drives, and so on, we will have a hardware abstraction layer which will abstract out the hardware for the kernel. So this will be the RTOS, the real-time operating system kernel, and then it will support a bunch of applications. So the board support package, which you would have seen along with the hardware abstraction layer, is the logical layer between OS and hardware, in the sense it ensures that the real-time OS, right, does not really need to be aware of all the details of the hardware. Some abstraction and some virtualization can be done. It is typically located in firmware in a read-only memory. It can contain device drivers. It can contain a bootloader to load the operating system. So pretty much what happens is, regardless of the device, if a standard interface is presented, then the real-time kernel will find it much easier to talk to this hardware, and also particularly with regards to determinism, timing, and jitter, it is also possible to have have constraints as well as guarantees embedded in such layers, such that higher level software can sort of have an idea of what are the worst case numbers it is looking at. So the board support package also contains built-in self-test routines, which is essentially low-level software to detect and report hardware errors. So we have discussed the raw hardware. We have discussed non-generic drivers, which are essentially drivers for the hardware over here with the board specific package, and some code which is processor specific, such that this layer completely abstracts out the hardware, such that regardless of the hardware, the upper level layer, which is the kernel, can execute, and then applications on top of the kernel. So this is how most of the popular real-time operating systems, such as VxWorks and QNX and so on, actually are written. So the key point is that we are sort of decoupling the hardware and the software. So regardless of the hardware that you can see over here, because of the board support packages and the drivers and so on, the basic WindRiver kernel is not that well coupled with the underlying hardware, which is a good thing. So this increases the life and the portability of the software. So most of the libraries can run on top of the abstraction layer over here. So furthermore, depending on the extent to which different hardware features, software features, etc. are available, we can arrange all the operating systems in a spectrum, starting from OSs that support hard real-time jobs to absolutely general purpose OSs such as Unix. So we can say that, look, we can have real-time operating systems in the sense that they are sold as real-time operating systems. They provide features for running programs in real time. So examples of them would be QNX, VxWorks, Linux. There is a real-time port of Linux known as RT Linux. So we'll discuss that in later lectures. And of course, real-time Windows, which at one point of time was called Windows CE as well. And then, of course, we have general purpose operating systems, which at best are soft real time. So they would be like Linux, Windows, and Unix, and so on. So it is important to understand that a large source of jitter actually arises from clock interrupts and their processing. So when we process the timer events, what we do is that we do certain set tasks, which is we process the event. We update the execution budget of the process in the sense we say how much time is left, update the current time, and so on. And then we update the ready queue in the sense we look at all the processes that are there to execute. And one flip side of timer interrupts is that the kernel can use them to also opportunistically schedule some of its own work, something that it has wanted to do for a long time, but it was not getting the opportunity. So the kernel can also do that. So in specific, it will look at the timer queue. It will look at all the tasks that are there along with their expiration times. So if let's say any timer event has occurred, in the sense that if there is any event whose time has lapsed, in the sense it needs to be handled right now, then the kernel will process all the timer events. So these would be like this timer is more like an alarm. Furthermore, it will update the execution budget of the tasks that are currently running, in the sense that let's say the last interrupt was 5 milliseconds ago and the new interrupt is now, and till this point of time all the processes have been running. So it will just update their execution times, just plus 5 to each. And if a task is not complete but its slice budget becomes 0, in the sense that what happens in many modern operating systems is that they use round robin scheduling for the same priority level. So what happens is that we want, let's say, one job to execute for 100 milliseconds, and once it is done, its current slice will kind of exhaust, it will become 0. So in this case, if the task is still not complete, we'll preempt it and we will run another task in a round robin fashion in the same priority level, of course, assuming that there are no higher priority tasks. So this is what this means. So this is when tasks will be preempted. Furthermore, we'll have to look at the ready queue. If there is a task which has a higher priority, then also the currently executing task will be preempted. So we had, of course, if you would recall, in an earlier lecture discussed the case of round robin scheduling, that let's say if there are 4 processors and there are 6 tasks of the same priority and also of the highest priority, then we decide a time quanta, 100 milliseconds in this case. We run a task for 100 milliseconds, then we preempt it, then run the next, and so on. If there is a higher priority task, of course, then as per EDF and RMS, a preemption is required, is necessary. Clock resolution. It is the time granularity provided by the clock. So it is possible to have clocks of a nanosecond granularity. But also you can have extremely high resolution timers, or you can have moderate resolution timers at the level of tens of microseconds or even milliseconds. So regarding clock resolution, of course there is a hardware clock, but the kernel also maintains a software clock. So in every time the hardware clock, let's say at the end of every millisecond or every 10 milliseconds, so this is known as a jiffy in Linux, a timer interrupt is sent. So this is when the software clock is updated. All right. So the reason is that if, let's say, any other thread wants to know the current time, it doesn't have to actually go and read a hardware register. It can just read a memory address. So that will give you the value of the software clock. A task can then read the time, which is the value of the software clock, using the POSIX function, which Linux supports, versions of Windows also support, called clock get time. Clearly, the finer the resolution of this, more frequent will be the hardware clock interrupts and the associated overhead, right? So the longer will be the amount of processor time that is spent on servicing them. So the response of the get time function as such is not deterministic, because there will be a variation. If, let's say, we are looking at a millisecond granularity for the software clock, there will be a variation of the order of hundreds of nanoseconds. But that's fine. If, let's say, our software clock has had the resolution of milliseconds, this is not something that should bother us. There are a few other mechanisms as well. So many modern processors provide a hardware timestamp counter. So this is basically a special kind of counter that is mapped to the memory address space of a real-time task. So a real-time task doesn't really have to make a system call and go through the OS to get the value of the time. It can directly read the value of the hardware timestamp counter from a given memory mapped address, and that will give it the time. So of course, here the program will have portability problems, in the sense that if it is working on one operating system, it need not work on another, right? Which does not, sorry, if it's working on one hardware or even one hardware software combination, it may not work on another if this feature is particularly not supported. So the timer service is clearly vital for most real-time systems. That is why we have spent so much of time talking about it. So if you would recall from the early chapters on scheduling, there are two kinds of timers, periodic and aperiodic. So the periodic timers are for all the periodic tasks, basically the ones that we have seen. All right, so basically RMS would fall in this. And then we have one shot, or we have a periodic timers, which are for these one-off jobs which just come. So the timers basically ensure that they don't miss their deadlines. So the periodic timers are basically used for sampling events at regular intervals or performing something periodically. So in this case, maybe to insert a job into the system or to read the value of a sensor, This is where periodic timers will be introduced to essentially introduce the periodic tasks into the system. Furthermore, once a periodic timer is set, it will also expire periodically. And we can also use this as an alarm kind of mechanism where if the periodic timer expires, we will call a handler routine. So, what could happen is that you set the timer here, you set it for some time, and when the timer expires, you see if a given task is completed or not. If it is not completed, it's a deadline miss, otherwise, it is not. Right? This is for cases where the period is equal to the deadline. In this case, what will happen is that as we have been discussing, we have these task specific queues. So, in this case, the data structure for the timer itself is added into the timer queue such that we can implement this method of creating periodic tasks. So then we have one-shot timers which expire only once. So they can be used, for example, to create any kind of a task or to monitor the time of any kind of a task which is aperiodic in the sense it appears just once. So it is typically used to see if and when a task misses its deadline. So the key point is that if let's say we have started a task and we want it to finish by some time, we set up an aperiodic timer. The moment it executes at that point of time, we can see if this given task has missed its deadline or not, because at this point we can check if the task has, let's say, completed over here, it's fine. If it has not completed over here, then it has overshot its deadline and it has missed its deadline. So, of course, some need will be there of initiating exception handling. So, this is basically we start a watchdog timer, we run the process, and then again, if the process ends, we stop the watchdog timer. But let's say, just in case the watchdog timer is not stopped and then the alarm goes off, the system will know that this process has missed its deadline. So, now let's do a brief survey of operating systems and look at their real time characteristics. So, Unix as such was developed way back in the late 60s, early 70s. So, Bell Labs and Berkeley did work on Unix. The graphical user interface system is still new to Unix. It had not come. It came only in 1985 with the arrival of the X Windows system. And then towards mid 90s, Linux came. So Linux always had a GUI. It always had a graphical user interface. So original Unix operating systems focused on heavy load and heavy throughput, right? They were batch processing systems. So things like fairness, progress, and resource sharing conflicts and sorry and resource sharing, they are not really on the lines of creating real time systems. So that is the reason traditional Unix is a real misfit for architecting a real time system. So in the Unix architecture, we of course have the hardware, a layer above the hardware, lots and lots of code for controlling processes, which includes the memory manager, the scheduler, and the inter-process communication, and the file system and device driver. So this is a very standard conventional structure that Unix has with process control file systems, and then of course a system called interface for user applications, right? So the data structures of Unix are also very standard, very conventional, where we have data structures for memory, virtual memory mostly. We have tables, page tables. We have I/O again. I/O devices need to be opened, managed, mapped to address spaces. We have I/O tables. The same holds for file tables, and for processes, we have a table that contains a list of all the processes that are currently running. And for each process, we have a process image, which of course stores pointers to the user data, user program, user stack, and so on. And for every thread that runs in user mode, there is another thread. It's a twin that runs in kernel mode. So the role of the kernel thread is usually nothing, but the moment a system call is made, the resident kernel thread, which was sleeping, right? That is You wake it up and you allow it to take over the task of the user mode thread, whatever it wants to do via a system call, and you get that done. So how does a process access system resources? Well, this is through system calls. This we know. So we have process control system calls, file system calls, and of course other specialized kind of system calls. So any traditional course on operating systems would deal with it. So we are deliberately not getting into the details of this process. So one interesting part in Unix is that we have multiple priority levels. So of course the system processes have the highest. So that would include the disk IO, the swapper processes, file processes, and then lower order kernel processes. And then among user level threads, we have a bunch of priorities where the priority levels are decided based on the priorities that are set, number one by the user and second by the super user. So super user is the root user where you can deliberately jack up your priority as long as it is within the set of user level priorities. So coming to Linux, it has had a different evolution, even though it has been heavily inspired by by Unix, but it started in the 90s, and the reason was that Unix was not really a PC operating system. So by that time, PCs had come up. So you needed a Unix-like operating system for PCs. So this is why way back in 1991, 31 years ago, Linus Torvalds, he used concepts of the existing Minix operating system, which was a toy operating system written by Tenenbaum, to make it more Unix compliant and to make it run on PCs. So that is how the entire Linux revolution started, and that was way back in 1991. But the good thing is that at least some degree of the internet had come by the mid 90s. So he was able to share the code and ensure that a lot of developers joined in and companies joined in, and it actually became a mass movement. So way back in 1994, support for TCP/IP, an enhanced file system, support for SCSI disk controllers, all of these things were added. So essentially, by the mid 90s, a functional Linux system started to get formed. So the Linux kernel as such is monolithic in the sense that all the kernel subsystems form a single piece of code. And there is no protection between them, or there is no boundary as such between them among the pieces of code. So modularity is supported in two ways. So one is that, of course, if you ever build the Linux kernel, you will see lots and lots and lots of options. So this means that at compile time, before compiling, we have a lot of options in the Linux kernel. And these options can be used to basically configure the behavior of the kernel. And also what happens is that dynamically we can load a lot of kernel modules, which are these small piece of code which are loaded pretty much like DLLs, pretty much like shared libraries. They are loaded into the runtime space of the kernel. So they are loaded into the kernel at runtime and on demand, and they provide different features. So for example, you can use such modules to have device drivers. You can use such modules to provide additional file systems to essentially augment different kernel components. It is doable. And we can have different minimal kernels that automatically adapt to the machine. And we can always, have a lot of modules that later on can be linked with the kernel to provide more functionality. So this will keep the monolithic kernel somewhat small. It will restrict its size. So from a code perspective, we have a monolithic kernel core. The moment we make a system call, we go to the kernel. The kernel may handle itself or may go to a module which implements the logic for the system call. Then the module will get loaded. So it will become a part of the kernel. It will service the system call and return the results back to the user process. There is a real-time Linux kernel. So this arose out of a fork from the regular Linux kernel. So here what is done is that we have different modules again. So the moment we have an rt load command within the kernel core, so here of course the kernel has to be specially built, but within the kernel core the real-time functionalities are activated. And so this itself, some of this code is there in a module state. So all of that comes in to the kernel. And the moment we have that, the existing Linux kernel actually becomes very small. In the sense, we don't use much of the kernel features, but we use more of the real-time features. And then, you know, the real-time features take over. So in terms of process scheduling, the way that Linux normally would do is that it would have round robin scheduling as we have looked at, and it would be preemptive in the sense every task is assigned a time quantum. So let's say time quantum q, let's assume 100 milliseconds. The moment 100 milliseconds completes, so then you will move to other tasks with the same priority. So this also has been discussed in the current lecture, and the priority per se is dynamically adjusted. So what happens is that we use a computed CPU usage factor, and we also take into account the base priority of the task. So in this case, real-time tasks have a base priority that is between 0 and 99, and user processes have a priority between 100 and 139. So the entry into the kernel would be like this, that we can have a synchronous entry where the kernel is going to perform some work on behalf of the process. So most of the time this would be through a system call, which is basically an API where you kind of send a fake interrupt to the processor and it will load the system call handler. The other happens because of some unusual action of the process, like a hardware exception, for instance. So then also the kernel comes into play. An asynchronous interrupt would arise if, let's say, the genesis of the interrupt is an IO device or even the real time clock, which is presenting itself as an IO device. So, in that case, it is not something that we request for, but it is essentially an independent event that happens on a separate IO device, and then the IO device sends an interrupt to the processor to raise its attention, to bring something to its attention. So the monolithic kernel that Linux has ideally looks like this, in the sense we have the hardware interface layer on top of it, which abstracts out the hardware. Then we have a bunch of drivers for the device, network, graphics, etc. And of course for the terminal, the one that you see. Along with that, we have other generic features like a memory manager, a process manager, and a file system, which essentially uses the storage drivers to talk to the storage hardware. On top of all of this, we have the applications which run in user mode. Another approach, which we will discuss again in the next two lectures, is that we don't adopt the Linux and Unix approach, because the key point is that in this case the kernel becomes huge, it becomes heavy. The kernel has a lot of its own work. Given the fact that the kernel has a lot of its own work, it needs to do all of that. And to do all of that, it becomes very heavy, and this is where real time guarantees start to matter less. That is why a good idea could be we keep the kernel as small as possible. We have a user mode where much of what was previously running in kernel mode actually starts running in user mode. One advantage is that basically now user processes and kernel processes roughly have the same priority, right? Kernel processes means erstwhile kernel processes. If the moment everything runs in user mode, they more or less run at the same priority. So it becomes much easier to give additional preference to real-time applications in such kind of a system. But of course, doing this and ensuring security and so on is a different challenge on its own. But as you can see in this diagram, the applications, the device manager, memory manager, network manager, etc., everything runs in user mode. So this is a typical microkernel kind of approach. So Windows is not pure microkernel, but definitely it is more of a microkernel than Linux. So this finishes this lecture. So in the next two lectures, we will discuss a large part of the operating system aspect of real-time systems.